High up in the Andes, right on the border between Argentina and Chile, something enormous has been hiding in plain sight. Not just a gold deposit, not just copper, not just silver, but one of the biggest metal discoveries on Earth in the last 30 years. The kind of discovery that quietly reshapes global supply chains without most people ever hearing about it. We're talking about a system holding roughly 12 to 13 million tons of copper, alongside tens of millions of ounces of gold and silver combined. At today's prices, that copper alone pushes past 150 billion Australian dollars. And once you factor in the gold and silver, the total in situ value climbs into the range of 200 to 300 plus billion Australian dollars. That's not profit, that's the raw metal value in the ground, but it gives you a sense of the scale. This isn't just a deposit, it's a resource capable of influencing entire industries. And yet, what makes this discovery truly fascinating isn't just the size, it's how it formed, because the geology behind it explains why it became so massive in the first place. To understand that, you have to start deep beneath the Andes, where one tectonic plate is sliding beneath another. This process is called subduction, and in simple terms, it's when a dense oceanic plate sinks under a lighter continental plate. As it descends into the mantle, it heats up, partially melts, and releases fluids. Those fluids are rich in dissolved metals, copper, gold, and silver, and they rise into the crust above. As they rise, they encounter large bodies of molten rock known as magma chambers. These chambers slowly cool over time, and as they do, they release additional metal-rich fluids into the surrounding rock. These fluids begin to circulate through cracks and fractures, depositing metals as they cool and react with the surrounding environment. This is how a porphyry system forms. For a non-geologist, a porphyry deposit is essentially a massive volume of rock that has been permeated by mineral-rich fluids. Instead of metals being concentrated in a single vein, they are spread throughout a huge area, often kilometres across and kilometres deep. At Filo del Sol, this initial stage of mineralization began around 15 to 14 million years ago. During a period of intense tectonic activity in the Andes, the system developed as a series of intrusions, bodies of magma that forced their way into the surrounding rock, creating a network of fractures and pathways for fluids to move through. These early fluids deposited copper and gold primarily in the form of minerals like chalcopyrite, which is a copper iron sulfide. They also created a characteristic alteration zone known as potassic alteration, where minerals like potassium feldspar and biotite replace the original rock. In simple terms, the rock gets chemically altered by hot fluids, leaving behind a distinct mineral signature that geologists can recognize. But that was only the beginning. Later, a second phase of fluid activity overprinted the system. These fluids were hotter, more acidic, and chemically aggressive. As they rose toward the surface, they began to dissolve parts of the rock, stripping away components and leaving behind a porous, sponge-like framework of quartz. This material is known as vuggy quartz, vuggy referring to the small cavities or holes left behind. This stage is called high sulfidation epithermal mineralization. Breaking that down, epithermal means it formed relatively close to the surface, and high sulfidation refers to the chemical state of the fluids, which were rich in sulfur and highly reactive. These fluids carried copper, gold, and silver in different chemical forms and deposited them in zones of intense alteration. This is where things get really important. The highest grade parts of the deposit are typically found within this vuggy quartz zone. That's because the aggressive fluids not only altered the rock, but also concentrated metals into these porous zones, effectively upgrading the system. Now, under normal circumstances, these two systems, the deep porphyry and the shallow epithermal, would be separated by hundreds or even thousands of meters of rock. You'd have to drill deep to reach the porphyry, and the epithermal system would sit far above it. But at Filo del Sol, something unusual happened. The entire region underwent significant uplift as part of the ongoing formation of the Andes. As the mountains rose, erosion stripped away a large volume of rock, on the order of 1 kilometre of vertical material. This erosion effectively collapsed the vertical spacing between the two systems, bringing them into close proximity. Geologists refer to this process as telescoping. In simple terms, it means that different layers of a mineral system have been compressed together, like pushing the sections of a telescope inward. The result is a vertically stacked system where high-grade epithermal mineralization sits directly above, and sometimes overlaps with, the deeper porphyry mineralization. This is why drill holes at Filo del Sol have intersected over 1 kilometre of continuous mineralization. It's not that the system formed as a single continuous zone, it's that multiple stages of mineralization have been superimposed on top of each other. And this is why the deposit is so large. But the scale doesn't stop there. Filo del Sol is part of a much larger geological feature known as the Vicuna Belt, a mineralized corridor stretching roughly 40 kilometres along the Andes. Within this belt, multiple porphyry and epithermal systems are aligned along a consistent structural trend. These structures, faults and fractures in the Earth's crust, act as conduits for rising fluids. They allow magma and hydrothermal fluids to repeatedly access the same pathways, creating multiple deposits along the same line. At Filo del Sol itself, the mineralization follows an 8.5 kilometre long alignment, with several centres of activity along that trend. This means you're not looking at a single isolated deposit, but rather a cluster of interconnected systems. This kind of structural corridor is a hallmark of major mineral provinces. The biggest deposits in the world tend to occur in belts, not as isolated anomalies. So what does it actually look like on the ground? If you were standing on the surface, you wouldn't see gold veins or obvious ore. Instead, you'd see broad zones of altered rock. Some areas would be bleached and clay-rich, others hardened and silicified. You might notice rusty staining from oxidized iron minerals, or bright blue patches of copper minerals forming near the surface. Below that, the rock becomes increasingly fractured and veined, with networks of fine quartz veinlets cutting through it. These veinlets are often associated with the porphyry system and represent pathways where fluids once flowed. Deeper still, the rock hosts disseminated sulfide minerals, tiny grains of copper and iron sulfides spread throughout the rock. It doesn't look spectacular, but when processed at scale, it contains enormous amounts of metal. Mining a system like this is a completely different proposition to traditional gold mining. There are no narrow veins to chase. Instead, operations focus on extracting and processing huge volumes of rock, often through open pit or large-scale underground mining. Because of the size of the system, even relatively low concentrations of metal become economically viable. And that brings us to the question of longevity. Deposits of this scale are typically mined over several decades, often exceeding 50 years depending on economic conditions and ongoing exploration success. Given that drilling at Filo del Sol is still expanding the known resource, it's entirely possible that its eventual lifespan could extend even further. There are also some fascinating geological features within the deposit that highlight just how dynamic it was during formation. One of the most important is the presence of hydrothermal breccias. These are zones where the rock has been shattered by the force of pressurized fluids and then cemented back together by mineral deposition. In simple terms, they're explosion zones underground. These breccias are significant because they often act as high permeability pathways, allowing fluids to flow more easily and concentrate metals. At Filo del Sol, they host both early porphyry mineralization and later high sulfidation overprints, making them key targets for high-grade zones. Another notable feature is the clear evidence of repeated mineralizing events. The system wasn't formed in a single pulse. Instead, it evolved over time, with multiple stages of fluid flow, alteration, and mineral deposition. Each stage modified and overprinted the previous one, creating a complex but highly enriched system. And perhaps most importantly, the entire system is tied to deep, long-lived structures in the crust. These structures have been active for hundreds of millions of years, controlling not just this deposit, but the broader mineralization across the region. That's why discoveries like this aren't random. They're the result of very specific geological conditions aligning over long periods of time. So while headlines might call this the biggest discovery in 30 years, the reality is that it's the culmination of millions of years of geological processes and decades of exploration work to finally understand what's there. And it's still not fully defined. Every new drill hole has the potential to expand the system further, to connect previously separate zones, or to uncover even higher grade sections. Which means that even now, this discovery is still unfolding. And that's the part most people miss, because the real story isn't just that this is one of the largest metal discoveries in decades, it's that we're only just beginning to see how big it actually is. I hope you found this as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.